Hello again, and welcome back. I'm very excited about today's lecture because we're going to see today perhaps the most important theorem in all of calculus, the fundamental theorem of calculus. You'll remember last time we looked at the problem of calculating the area under a curve bounded between numbers a and b. And then we generalized that problem to something called the definite integral. And I hope you agree with me that calculating that definite integral is pretty difficult. It used something called a Riemann sum, meaning we partitioned the area under the curve by vertical rectangles of width delta x, and the heights were determined by evaluating the function either at the left end point or the right end point or some other point. And then we added up those rectangles and took a limit. The number of rectangles approached infinity, or the width delta x approached 0. And if that limit existed, we called that the definite integral of our function. Again, that's pretty difficult to do. Today, we'll develop a formula that will allow us to calculate these definite integrals by using antiderivatives. This is the amazing intersection of the differential calculus that we're very, very comfortable with after many lectures, and these antiderivatives that we looked at 2 lectures ago. Near the end of the lecture today, I'll also try and give a little explanation as to why the fundamental theorem of calculus is true. But the first step, I think, is just to present the theorem and become comfortable in using it. So, what does the fundamental theorem of calculus say? Here's the setup. Suppose you have a continuous function on a closed interval ab. If you want to calculate the definite integral of that function, f of x, between a and b, here's all you have to do. Find an antiderivative of the function f. Any antiderivative will do. And with that antiderivative, subtract the antiderivative evaluated at the upper limit b minus the antiderivative evaluated at a. In other words, the definite integral from a to b of f of x dx is g of b minus g of a, where g is an antiderivative of f. It's pretty amazing. We don't have to do that limit process. All you have to do is find an antiderivative and plug in the endpoints. Let's do an example to make sure we're comfortable with what I just said. Suppose you wanted to find the definite integral from 2 to 4 of the function x. Okay, you can think of x as being the straight line y equals x. And this is actually an area problem. We're finding the area under that straight line between 2 and 4. In a minute, I'll look at the picture and show you that area. But let's now do the fundamental theorem of calculus. Well, what's an antiderivative of x? It has lots of antiderivatives, but perhaps the simplest is x squared over 2. Then you evaluate the antiderivative at the 2 endpoints. So g of 4 is 4 squared over 2, or 8. And g of 2 is 2 squared over 2, or 2. So we've evaluated the antiderivative at the 2 endpoints, and now we just subtract them to get our final answer. So the definite integral of the function x between 2 and 4 is g of 4 minus g of 2, or 8 minus 2 equals 6. Now let me make some comments about this process. To use the fundamental theorem of calculus, you have to be able to find antiderivatives. This theme will come up over and over in the next few lectures. You also don't need to include a constant of integration. Any antiderivative will do, and you just subtract them at the 2 endpoints. And finally, we'll see some examples where the variable of integration might not be x. Let me be specific about this. The definite integral from a to b of f of x dx is precisely the same as the definite integral from a to b of f of t dt, or f of theta d theta. That letter there is unimportant, because when you're finished finding a definite integral, the answer is a number. The variable evaporates. Now let me look back at that previous example. Remember, it was the line y equals x, and we were finding the area between 2 and 4. Well, you can sort of see how this is going to work. The area of the larger triangle is 1/2 base times height. That's 4 times 4 is 16 divided by 2 is 8. And then we subtract from that the area of the smaller triangle, which is 2 by 2 and divide by 2, so the smaller triangle area 2. And that 8 minus 2 gave us the answer to the problem 6. Good. Let's do another example to see how we are with calculating definite integrals using the fundamental theorem of calculus. And in a moment, I'm going to introduce some notation that makes it even easier. So let's find the definite integral of x squared minus 3 between x equals 1 and x equals 2. Okay, what's the first thing you have to do? You got to find an antiderivative of the function x squared minus 3. Well, how about x cubed over 3 minus 3x? Remember, you can always check your antiderivatives by just differentiating them. So that's a good antiderivative, because if I differentiate that, I come back with the original x squared minus 3. So I found my antiderivative, which I like to call g. And now a good notation is to put that antiderivative in brackets, and then on the right-hand bracket, down below, put the lower limit of integration, which is a 1, and on the top, put the upper limit of integration, which is 2. And then you take x squared minus x cubed over 3 minus 3x, and first plug in the 2, and you get 8/3 minus 3 times 2, which is 6. And then you subtract off the antiderivative evaluated at the lower limit of integration, evaluated at 1, and that turns out to be 1/3 minus 3. And then you simplify those pretty messy fractions. You get 8/3 minus 1/3 is 7/3, minus 6 plus 3 is minus 3, and 7/3 minus 3 is minus 2/3. A little warning here. These computations can be messy. There's lots of arithmetic involved, and even worse, there are a lot of minus signs, minus, a minus, a minus. This will come up a lot, so be careful with your minus signs here. Something else that's kind of interesting in this example, clearly we were not finding the area under a curve, were we? Because our answer was negative, and areas are non-negative. You can sort of see why this answer is negative. Imagine the original approach we did for the definite integral. Remember, the widths were delta x, and then we had those rectangles. Well, in this curve, x squared minus 3, we have a parabola, the parabola x squared, but it's been moved down 3 units. Hence, a lot of the parabola is below the x-axis. Hence, when you draw those rectangles, they aren't going up. They're actually going down for a while because they bump into the curve below the x-axis. So when you add up the function times delta x, you get some negative numbers, don't you? Some people like to call that negative area, but I don't like to use that term. Just be aware that a lot of times definite integrals can have answers that are negative. It could even be 0 sometimes. Good. I hope we're comfortable now using the fundamental theorem of calculus. How about a couple more examples? What's the definite integral of the cosine function between 0 and pi? Good. Okay. What's the plan? You have to find an antiderivative of cosine. What's that? Sine. Good. So you put sine in brackets and then put the 0 down below and the pi up above. You evaluate sine at pi minus evaluating sine at 0. Sine of pi, of course, is 0. Sine of 0 is 0, and 0 minus 0 is 0. That's kind of curious. The definite integral of the cosine function between 0 and pi, between 0 and pi turns out to be 0. I invite you to graph the cosine function on the interval 0, pi, and you'll convince yourself why the answer should be 0. Good. How about a little harder problem? How about secant squared x between 0 and pi over 4? What do you think? Well, we need an antiderivative of secant squared. How about tangent? Remember, the derivative of tangent was secant squared. So the integral, or antiderivative, of secant squared must be tangent. And then we evaluate tangent at pi over 4, and we get 1. And then we evaluate tangent at 0, and we get 0. So the final answer is 1. Good. Let me be very clear here about something. And this is often confusing to students, I think. The definite integral, which we've been evaluating today, looks like a to b of some function. That is always going to be a number. The answer is going to be a number as long as a and b are constants. You should think of that as generalizing the area under a curve, and it's going to be a number. Now, later on, that definite integral will represent other things like a volume or a surface area. But for the time being, keep in mind that it's going to be a number. On the other hand, antidifferentiation, which we did 2 lectures ago, is a function. The antiderivative of some function f of x is some other function. And that's because there are no limits of integration, are there? So there's a real difference here between the definite integral and antidifferentiation, even though they have the same symbol, that elongated s. And why did they use that symbol? Well, to calculate definite integrals by the fundamental theorem of calculus, you need antiderivatives. Good. Let me look now at a theorem involving definite integrals that I think you'll find kind of interesting. It's called the mean value theorem for integrals. Remember, we had the mean value theorem for derivatives many lectures ago. Well, now we have one for integrals. And here's how the theorem goes. If f is a continuous function on a closed interval, then there's some number c in that closed interval such that the following is true. The definite integral from a to b of f of x dx will equal f of c times b minus a. Let me show you a picture of what's going on here, and it'll be crystal clear, I think. Here I've drawn actually I drew a positive function here. It doesn't have to be positive. It could be negative or whatever. But I've drawn a function defined between a and b, and you can imagine has a certain area under that curve between a and b. The theorem says the following. There's some point c in between a and b, such that if you draw a vertical line from c, go up and hit the curve, and then go over, that's f of c. And what's the area of that rectangle? Well, the base is b minus a, and the height is f of c. Well, that's what the theorem says. It says the area under the curve is the same as some rectangle. That rectangle has the same area as the area under the curve. Kind of a neat theorem, isn't it? Once again, this is an existence theorem. It doesn't tell us how to find the number c. It just says that it will always exist. Good. Let me do an example to show you how to use this theorem, and then I'll give an interpretation as to why it's called mean. Not because it's angry, but for a different reason. So let's look at the function square root of x, say between 1 and 4. And if you integrate the square root function between 1 and 4, that definite integral should equal f of c times 4 minus 1, the difference in the endpoints, for some number c. Let's find that number c. So first I'm going to find an antiderivative of x to the 1/2, the square root function. That would be x to the 3/2 divided by 3/2. And then when I flip that fraction up, I get 2/3 x to the 3/2, and then I plug in my endpoints, which are 1 and 4, and I get 2/3 times, well, what's 4 to the 3/2? Oops, let's see, that's square root of 4 is 2, and then cube it, it's 8, and then plug in 1, you get 1. So the final answer is 14/3. So, according to our mean value theorem for integrals, there's some number c such that 14/3 equals f of c, which is the square root of c, times 3. And then you solve that equation. The square root of c is going to be 14/9, and c is then 14/9 squared, which is about 2.42. Here's a picture of what we just did. There's the square root function, and I've marked off between 1 and 4, and we discovered a number c that was about 2.42, and now I've drawn a rectangle of height f of c. So in other words, at c, I draw a vertical line, it bumps into the curve, and that forms a rectangle. And the mean value theorem for integrals says that the area under the curve between 1 and 4 is the same as that area of the rectangle. We like to say with this theorem that f of c, which is part of that theorem, equals 1 over b minus a times the definite integral. We like to say that f of c is the average value of the function f on that interval. That's the definition of average value. In our case, in the previous example, f of c is the square root of our c value, so it's 14/9. Now let me try to interpret this a little bit. Look back at the picture. Imagine you've got a lot of people lined up, and their heights go from 1 up to 2, say meters. So you've lined up all these people, and they kind of line up underneath the square root function. Well, what's the average height of all these people? Well, that's the average value of the function. So you sort of see that f of c is kind of the average height of that square root function between 1 and 4. Kind of an interesting theorem. Good. I'd like to look now at perhaps some more, as we say, interesting examples using the fundamental theorem of calculus to make sure we're comfortable with some of the difficulties that might occur. For example, let's find the definite integral between 0 and 4 of the absolute value of x minus 3. Well, between 0 and 4, the absolute value of x minus 3 is kind of complicated because sometimes x minus 3 is positive on that interval and sometimes it's negative. More particular, the absolute value of x minus 3 equals x minus 3 if x is greater than or equal to 3, and then it's minus x minus 3 if x is less than 3. That's the definition of the absolute value function. So how am I going to calculate the definite integral between 0 and 4? Well, remember that theorem where you can split up an integral into two pieces? So first I'm going to integrate from 0 to 3. And on that interval, I'm going to integrate 3 minus x. In other words, minus the quantity x minus 3. And then on the interval 3 to 4, I integrate the function x minus 3. So you're integrating two different functions here. One is the negative of the other, taking into account that the absolute value function is kind of complicated when the thing inside is negative. So now I have two integrals, each of which can be evaluated very quickly. The first one, the antiderivative, is 3x minus x squared over 2, and I plug in the limits 0 to 3. And the other one is x squared over 2 minus 3x, and I plug in the limits 3 to 4. And then if you do all that arithmetic, it's kind of messy, it takes a while, and add it all up, you get the answer of 5. Let me show you a picture to convince you of that. Here is the absolute value function of x minus 3 on the interval 0, 4. Notice that it's our friend the v of the absolute value function, but it's been shifted to the right 3 units. Good. We just calculated the area under that curve because the absolute value function is non-negative. And we got the answer of 5. Does that make sense? Well, the left-hand piece is a big triangle. Its area is base times height divided by 2, which is 9 over 2. And then the right-hand little triangle is 1 by 1, so that's a half. 9 halves plus a half is 10 halves, or 5. So our answer seems correct. Good. So I think now, hopefully, we're comfortable using the fundamental theorem of calculus if we can find those antiderivatives. And again, that's a big question there. Can you find antiderivatives in order to use the fundamental theorem of calculus? But for the time being, the problems have been such that we could find them. I'd like now to spend the remaining portion looking closer as to why the fundamental theorem of calculus is true. This is sort of a proof, and normally in elementary calculus we don't do many proofs, but this is a good one in the sense that we'll see why integration and differentiation are connected, why one is kind of the inverse of the other. They involve each other, they're tied together, something you wouldn't expect. Historically, the integral problem is much, much older than the tangent line problem, and yet here they are connected. So let me step through the proof. Let's suppose we have a function, and let's assume it's non-negative to make things simpler, and I'm going to define capital A of x to be the area from little a up to x under that curve f. Now I'm going to use f of t rather than f of x because I'm using x as my upper limit of integration. Here's a picture of what I'm talking about. We have our graph of f, and on the t-axis, which is the horizontal axis, the graph starts at a, and then I've drawn it out to x. And capital A of x is the area under that curve between little a and little x. Good. Now, let's move to a nearby point, x plus delta x. Remember, delta x is always kind of a small change in x. So we move to x plus delta x, and now we have the area starting at a and going out to x plus delta x. Well, what would that area be? According to our symbols, it would be the integral from a to x plus delta x of our function f of t. Good. Now, let's subtract these two. That would give the area of that skinny little rectangle of width delta x, and the height is determined by the curve between f of x and f of x plus delta x. So now I'm calculating the tiny strip determined by x and x plus delta x. So I'll call that delta A, change in area. And it's going to be the integral from a to x plus delta x minus the piece from a to x. Take the big piece all the way out to x plus delta x, and then take off the smaller piece, and you're left just with the strip. Good. Okay. Now look at our picture here for a moment. I'm going to let little m be the minimum value of f on that little strip x to x plus delta x. In my picture, little m seems to be the distance up from x, but the function could be decreasing there. But let m be the minimal value of the function on that small interval, and let capital M be the maximum value of the function on that same interval. What do you notice about little m and big M? Well, again, let's look at the picture. Little m determines a rectangle, height little m, width delta x. That's a certain area. Big M determines a larger rectangle, height big M, width delta x. And I claim the area under the curve is in between those two maximal and minimal values. Writing it as an equation, m delta x, that's the area of the small rectangle, is less than or equal to delta a, that's the area under the function between x and x plus delta x, and that's less than or equal to big M times delta x. We've sandwiched the area under the curve between two rectangles. One is smaller and one is larger. Now divide all three sides of this inequality by delta x, and you have little m less than or equal to delta a over delta x less than or equal to big M. Now, let's take a limit. Let delta x get closer and closer to 0. That means that my rectangle there is getting skinnier and skinnier. What's going to happen? What's little m going to approach? Well, it's going to approach f of x. What's big M going to approach? It's also going to approach f of x. What does that mean the thing in the middle approaches? Well, it's kind of in a sandwich here. We call this the squeeze theorem or the sandwich theorem. We have f of x less than or equal to the limit as delta x goes to 0 of delta a over delta x less than or equal to f of x. Hello, it's in between the two of them. It must be equal to them. Hence, the thing in the middle equals f of x. Well, who's that thing in the middle? That's the definition of derivative. That's the derivative of a with respect to x, or a prime of x. That's the definition of derivative. So what do we have? We have a prime of x equals f of x. Good. That means we can now find an antiderivative. A of x will be some g of x plus a constant, and g will be an antiderivative of f. Good. Can I find the constant c in my equation? Well, we know one more piece of information. What's the area from A, starting at A, to A? 0. So that means that big A of little a equals g of a plus the constant, and that has to equal 0. That tells me that my constant is minus g of a. So we're almost done. I hope you've kept up with this. It's a tough little proof. We finally have that the area function is the integral from a to x of f of t dt. That's how we defined it. And it's equal to g of x minus g of a, where g is an antiderivative of f. Now replace x with b. So you have from a to b, f of t dt is g of b minus g of a. And remember, I said you can use any letter you want in these formulas. So why don't we get the final line? The integral from a to b, f of x dx is g of b minus g of a. Wow, that's the formula in the fundamental theorem of calculus. That's a tough theorem to prove. There are many other proofs in textbooks, but this one kind of shows you, I think, how the derivative comes into play when you're looking at the area under a curve. Good. Next time, I'd like to continue looking at the fundamental theorem of calculus. It's so important that we're going to devote 2 lectures to it. We'll see yet another relationship between integrals and derivatives, how they're tied together. And then a little later, we'll look to the issue of how do we find these antiderivatives. That's big business. A lot of calculus courses, especially at universities, spend weeks on calculating antiderivatives. So I look forward to seeing you next time when we continue our discussion of the most important theorem in all of calculus, the fundamental theorem of calculus. Thank you very much.